Well, thank you for coming to another lecture for the Introduction of Computer Graphics. Introduction to Computer Graphics. So today, we're going to talk about curves. So curves, this is actually a big topic, one of my favorite things in computer graphics. I love curves. And I'm going to tell you a lot about curves, but I want to start with talking about why do we care? Why do we care about curves? We care about curves because they're pretty much everywhere in computer graphics. Sometimes they're right in front of you, but sometimes they're sort of hiding in the background. You don't quite get to see them, but they're there, and they're really making a lot of things happen. For example, one of the big places where curves show up is for representing sort of thin and long objects. Kind of makes sense, right? Hair is a very good example for that. Hair models used in computer graphics almost always use some type of curves. Another thing is cloth models, right? So cloth is made out of, a lot of cloth is made of yarn, and yarn is, it's a thin, long object. So if you have yarn level cloth models, we represent them using curves. Or fiber level models, we represent them with curves. Or things like carpet or grass. So all of these things use curves for representing them as models. But curves also show up in other places. For example, we have animation curves. So whenever you're defining some animation, we connect different keyframes with curves. We're going to talk about keyframes and all that and how the animation is done. So if these examples don't make too much sense to you, don't worry about it. But the curves are in the background for applications like that, where we're sort of interpolating different parameters or different values. And another application of curves is, for example, when you're displaying graphs, right? This is not necessarily computer graphics, but they're using computer graphics as well. But, it's an application of computer graphics in some ways. So, curves can show up in so many places. And a lot of 3D models are prepared using curves. Not all of them, but, a lot of them are actually prepared using curves, even when the result is not necessarily a curve model. So our topic for today, actually our topic for this whole week, is going to be curves, and we're going to implement a specific type of curve formulation in our projects related to this topic and our previous topic, which was WebGL. Right? So, yeah, curves are great. They're very, very important, and they're relatively simple. So we're starting with curves, then more complicated stuff. So let's think about 2D first. The concepts that I'm going to tell you will extend to 3D and even higher dimensions, but let's start with 2D. In 2D, for any point, I have X and Y coordinates, right? For a curve is going to be a collection of points, and each point will have X and Y coordinates. Okay, that doesn't tell me much. So we're probably going to have some relationship between these X coordinates and Y coordinates, right? So for example, probably the most familiar thing to us is something like this, like a function representation. The Y coordinate is a function of X, right? F of X. So, we can just draw it. We can just say, what's the simplest thing we can get? For example, a line, right? A line that's passing through the origin, right? So that's a kind of curve. It's not very curvy, but technically it's a kind of curve, I guess. So, what's the function for that? For this specific case, turns out it's y is equal to 2x. It gives you this. All right, simple enough, right? Of course, you can change that too and change it to some other value. Let's call it a. That changes the slope of the curve. And if I want to move this curve somewhere other than passing through the origin here, I can just add some value to it, and it just moves it up or down by adding some value c over here. All right. So this is a curve. Sorry, it's a line with this very simple function. But functions can be pretty much anything, right? I can represent pretty much anything with a function, but not really everything. So when I'm representing a curve using a function formulation like this, I'm actually limiting myself quite a bit, because not every curve is a function that can be represented like that. Now, this sounds very general, but it actually isn't, because this functional representation means that for each x value, I am going to get one and only one y value here. Right? That's how this function representation works. So if I take this curve and I rotate it, and it looks something like this. Now, this is not going to be a function anymore, because let's pick an x value here. So for this x value, I have three y values, right? So I cannot possibly represent it using this like a function like this. So this is not a very nice general representation, but I wanted to start there because that's probably the most familiar thing to us. You must have seen functions like this a lot of times in the past, so that's why we're starting there. But we can do something similar to this, right? I can take this function and I can make it as sort of like a 2D function. I can make it a function of x and y, and I say x and y is equal to 0. So it's a function of x and y that's equal to 0. So this is what we call an implicit representation of a curve. So any point in space that satisfies this equation is a member of this curve. So basically any point in this curve, this means that any point in this curve will satisfy this equation. And that's an implicit representation. It's going to be an equation like this, and it's going to say whatever satisfies that equation would be at part of the curve. All right, let's go back to line, because line was simple. And let's see that an implicit representation of a line, right? So think about this line. The implicit representation of a line, well, this was our equation. If I want to get the implicit representation, I can just move y to the other side, and there it is. There's my implicit representation of this particular line. But in general, I could have y multiplied with something like some constant as well. So this is a very general representation, a general implicit formulation for a line. You can represent any line using a formulation like this. Again, just an implicit representation. But it doesn't have to be a function like this. We could be using more complicated functions. So when we say implicit representation, we're talking about something that looks like this, a function of x and y, some function that contains x and y, which is equal to 0. All right? And this is going to be more powerful than just a f of x kind of representation, because here, for example, we can have something like this. We can have a circle, right? So what's the implicit representation of a circle? You must have seen it a million times before, right? It looks something like this. X squared plus y squared minus r squared is equal to 0. Sometimes we write it as x squared plus y squared is equal to r squared, but it's the same implicit formulation. But we like to write it like this so that the result is equal to 0. That's the typical way of writing it. You don't necessarily have to, but they're sort of equivalent anyway. Okay, well, this is a circle that is centered at the origin. What if I want to move the circle somewhere else? How do I do that? If I move the circle over here, then the equation is going to change just a little bit, right? And it's going to be this, x minus cx and squared, y minus cx and cy squared, and c is the center point here. It's the same equation, just translated, basically. So, all right, so this is an implicit representation, and our curve can have pretty much any shape, and I'm going to have a function, an implicit representation that gives me this. Now, I like the vector notation. I don't quite like using this x, y notation that much. I like using vectors because that sort of simplifies notation a little bit. Let's do that. Instead of x and y, I'm going to put this bold x, and so this is a vector. In 2D, it's going to have basically in 2D, it's just going to have this x and y coordinates. This is what I mean by bold x vector. It's going to have these x and y components. In 3D, it can have x, y, and z components. So basically, this function looks like this always. All right, so this is our implicit representation. Now, implicit representations are very, very useful for a lot of things, but not for everything. They're sometimes a little inconvenient. For example, if I wanted to draw this curve based on this implicit representation, what do I need to do? I need to find all points in this xy space that satisfy this equation, whatever that is. Now, I can't possibly look at all points and see if they satisfy this equation, right? There are infinitely many points here. I kind of need to figure out a way to do something more clever. But this way of looking at a curve is not being particularly helpful to me, right? It's not telling me how I can draw this curve. And a lot of times in computer graphics, big surprise, we like drawing things, right? So I want to be able to draw this, and I want to be able to draw this efficiently. So this representation is not going to be very helpful to me. I mean, it is helpful for a lot of things, and it's helpful for a lot of things in computer graphics as well, but not for most things. For most things, we prefer using a different representation that of the same curve maybe, but it's a different way of representing the very same curve. For example, I could have a function that tells me what that vector is, and the function is going to get this scalar t value, and based on this t value, it's going to spit out this a position on that curve. So we can think of this t value as like time, and imagine that I'm drawing this curve and t is giving me the time. And this kind of representation, we call this a parametric representation. It's a parametric representation, and t is going to be our parameter. So this is not exactly time. We're not talking about animation and things are changing. But just imagine that if I'm going to draw this curve, if I want to draw this curve by hand, I am going to start somewhere, right? If you give me a marker and tell me to draw this curve, I'm going to, take it and draw it like this, right? So I'm drawing this curve. I start somewhere, right? Let's say the place I start is going to correspond to the t value 0, all right? So that point over there is f0, right? And I continue drawing, and by the time I reach the end, this endpoint, let's call this point is f1, right? So I start drawing my curve, and I start from here, and I end up here. And in this parametric representation, any value of t between 0 and 1 is going to give me a position along this curve. Right? So I'm not telling you what that function is. I'm just saying that in this parametric representation, I will have a function that will give me a position on the curve based on this t parameter. Right? So you can see that this parametric representation is actually very, very powerful, because it's directly giving me the solution of this implicit representation. So I don't have to solve this equation in the implicit representation. Instead, I'm just using this function. I'm just giving it a t value, and it's giving me back a position on the curve. So that's great. That's very, very convenient. Because of that, the parametric representation is what's really popular in computer graphics. We do use implicit representation for certain things. In some cases, it kind of makes sense to have an implicit representation of curves or other things. But a lot of times, we're going to be using the parametric representation. It's a lot more popular because it's just directly giving us the solution. Right? So, very good stuff. Now, I want to mention something here. I've sort of arbitrarily picked and said, this is going to be 0, and this is going to be 1. I could pick whatever values I wanted. This could be, I don't know, 5, and this could be 17. I just pick some value. Of course, if I'm going to get the same curve shape, this function will be different depending on, So if I would like f0 to be at this point, then I will have a particular function. Or if I would like f5 to be at this point, I will have a different function, right? And they might be representing the same curve. They might be representing the same shape, but the function itself is going to look a little bit different because its output is going to be different. Right? Another thing is that, okay, let's say that this is always f0, but maybe this point is going to be f1 or f2. F at t is equal to 1 or f t is equal to 2. If it is f t is equal to 1, then as I increase t, I'm going to moving along this curve with a certain speed. If I said that, oh, I'm going to change this function such that f is equal to 2 will be at this point, then I am going to be moving along this curve a little bit slower as I increase my t value. Because the t value needs to come all the way to 2 by the time I reach to this point. So this is, oftentimes we call this as like the parametrization of the curve or reparametrization of the curve. So you can take any curve and reparameterize it. It's still the same curve. It's just that you change how you enter the t value to the curve. Reparameterization is this, like I have a function, but I'm changing such that it produces the same value with different inputs. That's going to be a reparameterization of the curve. It's going to be the same curve with the same shape. It's just how the t values appear along this curve is going to be different. But it's not like I'm seeing the t values here when I look at this curve, so who cares? You might care. In some cases, you might care. Maybe you're animating something and it's moving along this curve based on t and you're using t as actually time. In that case, you might care, right? But the most important thing for you to understand here, and the reason why I'm spending so much time here, is to show you that I have this sort of independent variable here that is t. And I can change how I interpret t without changing the shape of this curve. So in some ways, I'm adding this extra dimension to my representation. An extra time dimension, if you will, to my representation. And that's not saying anything about the shape of the curve. Okay? So that's just this additional t parameter is creating for me. But because I'm representing my curve like this, unlike implicit representation, this one is just giving me the results, the output, the solution of this implicit representation is giving me that solution directly. Right? So that's what's really nice and powerful about the parametric representation. But in addition to x and y, now I need to, sort of worry about this t. All right, let's move on. Well, we'll get back to things that will be related to this. All right, so let's start simple and let's say let's look at this line. So we said that implicit representation of this line was in the form of ax plus by plus c is equal to 0, right? So in this very case, in this specific case, it's going to be this equation. X minus 2y plus 2 is equal to 0. That sounds about right, I guess. I mean, when x is 0, y is over here. When x is 0, if I put 0 here, minus 2y plus 2 is equal to 0. That means y is 1. All right, that means that this point is 1, right? So 0, 1 is at this point. So probably the slope is right. So I guess this is correct. So what's the parametric representation? The parametric representation for this is going to be two functions, not just one, because it's going to give me a vector, right? It's going to give me both the x-coordinate and the y-coordinate based on t. So if you look at these two equations, on the right-hand side, I'm not going to be seeing any x or y here. I'm only seeing t here. I'm only seeing t here, right? So it's because that's a function of t. And its output is going to be my x and y coordinates. So that's the parametric representation. So because it's outputting a vector, I can write it as two separate functions here. And it's really okay to think about a parametric representation as a series of functions. In 2D, it's going to be 2 functions. In 3D, it's going to be 3 functions. If you go to higher dimension, it's going to be more functions, right? It's okay to think about it that way. Let's see. Is this the correct parametric representation, though? Let's see. What happens when t is 0? If t is 0, x is 0. If t is 0, y is 1. So I get this point. All right, that's correct, right? All good. What if t is 1, I get x2. If t is 1, over here I get y2. So 2 is going to be the other one. Yeah, that sounds about right. Is that a solution to this implicit equation? Let's see. If x is 2 and y is 2, there's going to be 2 minus 4 plus 2 is going to be 0. Yes, so that is actually a solution to our implicit equation. So these 2 representations, they're the same thing. But this one is not being very helpful to me because it's not giving me the solutions. This one is doing very, very helpful. I'm just, adding a t-value to it, and it's giving me the x and y coordinates. All good. Okay, that's why we like the parametric representation. We like showing everything using parametric representation. Well, the only thing I don't like here is that now I have 2 functions, and I don't quite like to look at it as 2 functions because this is actually just one function in disguise. It's just a vector function, right? So let's take these 2 functions and write them as one function. So it's going to look like something like this. So my output is a vector. So t is for x multiplied by 2, for y it's multiplied by 1, plus for x I'm not adding anything, for y I'm adding 1. So it's basically these 2 functions, I just wrote them in this vector form. And for a line, this is actually quite typical. So imagine a line that goes through 2 points. Let's call the first one P0, the other one P1. In this specific case, P0 is going to be 0, 1, and P1 is going to be 2, 2. So I can write the equation of this. I can write the parametric equation for this line as this. P0 plus t times P1 minus P0. So what does that mean? Let's take a look at this for just a little bit. Let's see if this is correct first. So P0 is this term, right? Is it 0, 1? Yeah, it is 0, 1. That's good. How about P1 minus P0? P1 minus P0 is supposed to be 2, 1. 2, 2 minus 0, 1, that's going to be 2, 1. So it's all good. So this is correct then. All right. So this is a very, very helpful way of thinking of lines. I really like this sort of representation for lines. And it really has 2 parameters. It has a point on the line and a direction. So a point on the line, in this case, that point is P0. The direction is P1 minus P0. That means the vector that starts from P0 and goes to T1. So this vector starting from P0 to P1 is going to be the direction. So I have a point in space and the direction that obviously defines a line, right? So any point, and I can pick any point along that line by changing this t value. When t is equal to 0, I'm going to be at P0 here. When t is equal to 1, I'm going to be at P1 here. If t is greater than 1, I'm going to move along this direction. If t is smaller than 1, I'm going to move in the opposite direction, right? So, all good. Right, this is a very, very helpful representation for a line. So let's use that. Actually, let's write this in like a polynomial form a little bit. I'm going to put the t over here and the constant over. I just shifted things around. And I like writing it in this form, even though it looks a little less intuitive. It's just the same equation. We just move things around. But it's instead of this, keep writing this x. X is any point along this line, right? So instead of keep writing x, I'm going to say this is a function of t. So as a function of t, for any t value, I get a position out of this. And it's I'm writing this as like a bold function because it's supposed to produce a vector. All right. So in general, a line, I can write it as a polynomial of this form. Right, so this is a parametric representation of a line as a polynomial of degree 1. That is, at plus b is going to give me a line. Now, in this case, a is p1 minus p0 and b is p0. But there's another way of thinking about this. I can also think about this as like a linear interpolation between these two values. Linear interpolation between p0 and p1. Like if I were to linearly interpolate between these two, then linear interpolation will look like something like this, right? So 1 minus p times p0 and t times p1. That means when t is equal to 0, I'm going to be at p. When t is equal to 1, I'm going to be at p1. So between 0 and 1, I'm going to be along this line segment. So I'm linearly blending these two terms. And what's important here is for you to immediately notice that the terms, the weights of P1 and P0 and P1, they add up to 1. Right? That's very, very important actually. So I'm just blending two values here. I blend the P0 value and P1 value with two different weights. One of them is using 1 minus t, the other one is using t. And as long as these weights add up to 1, I'm going to get a line that passes through P0 and P1. So there are different ways of blending them. This is just a typical linear interpolation function. But I could be using different things as well. Well, what's really important here is to see that these two weights always add up to 1, regardless of what the t value is. So in this way, I have a linear interpolation. Now, if you look at these two equations, you will see the connection, right? This is exactly the same equation. I just shifted the terms around. What's really helpful here in this notation is that P0 and P1, they appear only once. And now conceptually, when I look at this, I'm thinking about this line as a linear interpolation between these 2 points. Now I'm emphasizing this a little bit, even though it may seem a little obvious to you, at least to some of you. I'm spending a bit of time here because this is the right way of thinking about this, and it's going to be very, very helpful to understand more complicated curves that don't quite look like line segments like this. All right? But so in general, I can write a curve as a line as a linear interpolation like this, as something that goes through P0 and P1, or 2 points in space. Or I can write it as a polynomial. There are equivalent representations. And I can take one and convert it to the other easily. Right? Just a few algebraic manipulation, and I get the other one. Okay? Alright, let's get something a bit more complicated. Let's take a look at a polynomial, a higher degree polynomial. Instead of a polynomial of degree 1 here, let's take a look at a second degree polynomial. So what is that going to be? Something like this. So a second degree polynomial is going to give you the shape of a parabola. Now this is sort of a rotated parabola. So if you write it in like a y is equal to fx form, this may or may not work depending on how you rotate the parabola, but it's the same shape. It's the shape of a parabola. It's, y is equal to x squared. That shape, it could be rotated and scaled and translated, but it's still the same original shape. And it's going to look like something like this, right? It's going to be, the polynomial form is going to be a t squared plus bt plus c. That's going to give us a curve that looks like something like this. Okay, I mean, yeah, it's fine. I have a vector for A, a different vector for B, a different vector for C. But this representation is not very intuitive, is it? I mean, I look at it and I have this curve. I mean, it's a parametric representation. It's very useful. I can just stick a t-value here and it tells me where the curve is going to be. But if I want to draw this curve that looks like this, it's not immediately intuitive. It's not immediately obvious what values I should pick for A, B, and C, right? It's a little, not very helpful. All right, let's come up with something that's going to be more helpful here. So what I'm going to do is that let's say that I'm only interested in this part of this parabola, this part of this polynomial curve. The curve continues to infinity on both directions, but I'm only interested in this finite segment of it. So what I'm going to do is I'm going to say that t is equal to 0. At t is equal to 0, I'm going to be at this point, at the beginning point. And at t is equal to 1, I'm going to be at this end point. Okay, I just arbitrarily pick these 2 points. Now, here's the trick. What I'm going to do is that I'm going to look at the tangents of this curve. The tangent direction. So what's the tangent of a curve? It's a line that goes through the curve at a point and has the same direction as the curve at that point, right? That's going to be the tangent line. So if I draw the tangent lines for these 2 endpoints, the beginning point and the ending point, these 2 endpoints, I'm getting somewhere with them. They're going to intersect at some point. Let's mark this point as well. These 2 tangents intersect at that point. Now I'm going to mark these. I'm going to name these points. I'm going to say this one's P0, this one's P1, and this one's P2. Like, why did I do this? Why did I do all that stuff? I didn't do this because now I can write this, the equation for this curve, this quadratic curve, a second degree polynomial curve, in this form. Alright, this looks a little funny. But yeah, this is the equation. So if you want to know what the equation of this curve is, it's that. Alright, so it's P0 minus 2P1 plus P2 is going to be the t squared factor. And then the t factor is going to be 2P1 minus P0, and the constant term is going to be P0. That's the point where we started. Well, this is sort of symmetrical, right? So I could just, I could say that this point is going to be my starting point and this point is going to be my ending point. I could look at it in the opposite direction, in which case P0 and P2 would switch places. But then when t is equal to 0, I would be here, right? In this form, when t is equal to 0, I'm at that point. When t is equal to 0, this term drops, I'm only left with P0. So this is the equation for this parametric curve. That's a second degree polynomial. Okay, this is the equation. Very nice. Not very nice, is it? You kind of need to remember all these stuff. There is a much nicer way of writing this polynomial. Remember how we wrote the first degree polynomial? That was a line as a linear interpolation of 2 points. We can do something similar for a second degree polynomial as well. So we can write it in this form. In this form. So I can this is like a second degree interpolation of these points. And not exactly interpolation, because it's only interpolating P0 and P2, but not P1. So this turns out to be a function like this. It's 1 minus t squared plus 2 times 1 minus t P1 plus t squared P2. And in this case, my P0, P1, and P2, these 3 points, each one of them will appear only once in this notation, which kind of cleans things up a little bit. And if you look at the t values here, they're kind of nice. That 1 minus t squared, the other one is 2 1 minus tt, and the other one is t squared. Right? It's a very nice way of looking at this. So we like this because I can easily write this if you give me 3 points. If I say, well, define a curve based on 3 points like this, I can easily spit out this formula. Fairly easy, right? This is what we call the Bézier form of this quadratic polynomial. So I can take this polynomial and convert it to this form, just like I did for a line. Or I can take this polynomial and take this Bézier form and convert it to this one. But we kind of like this version a little bit because it looks a bit more intuitive. So that's what we're going to use. So this is the definition of a quadratic Bézier curve. Quadratic because it's a quadratic polynomial. That means it's the degree 2. And it's going to be defined by 3 what we call control points. There's going to be point P0, P1, P2 are the 3 control points that define this quadratic Bézier curve. So with all this long explanation, I'm hoping that you understand one thing that is very, very important. Bézier curves, probably the most popular curve formulation used in computer graphics. Bézier curves are nothing different than polynomial curves. It's just a polynomial written in a special form, such that each one of my control points will appear only once. So it's basically a blending of these 3 control points. That's what it looks like. But it's basically just a polynomial, right? So I can always convert this to a polynomial. And I don't have to use just 3 points. I can add more points. So I can add a 4th point. But if I add a 4th point, I'm going to need a higher degree polynomial if I want to mix in a 4th point, sorry. If I add a 4th point, I can do that. Actually, I can represent the very same exact curve with the very same shape using a 3rd degree polynomial. You can always do degree elevation. You can always take a 2nd degree polynomial curve and represent it using a 3rd degree polynomial. So in this case, I'm representing the very same curve with 4 control points, P0, P1, P2, and P3. And this is going to be my cubic Bézier curve. And the cubic Bézier curve is going to have 4 control points, and it's going to look like this. Again, it starts with 1 minus t cubed this time, and then 3 times 1 minus t squared t, and then 3 times 1 minus t squared, and then t cubed. I said, I'm getting the very same curve here. Like, what's the point of using a degree 3 polynomial if I'm going to get the same curve? I don't have to get the same curve, right? Now I have 4 control points. I can just move them around and get a shape that does not look like a parabola anymore, right? So yes, 3rd degree polynomials can exactly represent a parabola shape, but they don't have to. They can represent more stuff. In fact, quadratic Béziers using only 3 control points will be planar curves because 3 points in space will define a plane, right? Actually, in whatever dimensions you use, 3D or higher dimensions, you pick 3 points, they're going to define a plane. So the curve that is defined by these 3 points will be a planar curve. It's going to be a curve that's going to be on that plane. But when I define a curve using 4 control points, these cubic Bézier curves, 4 control points, they don't have to be on the same plane. So this is not necessarily a 2D curve. This can be a 3D curve if I move one of these points out of space, like move one of them closer to you. And that's not going to be a planar curve anymore. So, which is why this form of Bézier curves is probably the most commonplace formulation used in computer graphics, because oftentimes we're interested in the 3D, and 4 control points will give you access to 3D, so we're all good. So going back, I said this is the most popular one, but of course we have the quadratic formulation, we have the linear formulation as well. So you can think of this linear interpolation as like a 1st degree Bézier curve. Although I don't believe anybody calls this as a 1st degree Bézier curve. This is just a linear interpolation. right? It's a lot simpler to just call it linear interpolation. But, if you had a first degree Bezier curve, this is what it would look like. It's a line. This quadratic formulation, this is the cubic formulation. And for those of you who've noticed the pattern here for these terms, that's the Pascal's triangle, yes. So I can have, I have dot, dot, dot here, I can have higher degree polynomials, and that means that I can have higher degree Bezier curves. And they all can be written in this form. So these are our typical Bezier curves. So when people tell you, I'm using Bezier curves, they mean cubic Bezier. If they're specific, they may say, oh, this quadratic Bezier, then that means second order Bezier. If they mean anything else, they typically have to specify a fourth order, fifth order, sixth order, nth order, whatever. And sometimes people do use really, really high order polynomials for representing curves. Because the thing is, these are polynomials. So they can only represent polynomial functions. They can't represent shapes that are not exactly polynomials. Can you think of an example that will not be a polynomial? A very common example? I even showed an example. Yes, well, sine, yes, that's one. But a very, very common example is a circle. You cannot get circles with polynomials. But turns out, with cubic polynomials, we can approximate them well enough. For a lot of purposes, they're very, very close. They're not exact. But, visually they're close enough, so they're okay. So most of the time this is what we use. But if whatever you're doing is really sensitive to getting certain shapes, like a circle, for example, then, this third order polynomial representation is not going to be very helpful. But don't worry about it. We're going to talk about some other representations that will allow us to do that, but we can't do that with polynomial curves. So regardless of which ordered polynomial you pick for your Bezier curve, they will have certain properties. So I want to go through those properties. The first property, probably the obvious one, is that a Bezier curve is going to interpolate the first and the last control point, but not the intermediate control points. So the intermediate control points will define the shape of this interpolation, but it's only going to interpolate the first one, and it's going to interpolate the last one. And this is very, very important because a lot of times you may want to specify exactly where the curve is passing through. These middle control points are going to be a little unhelpful to that, because the curve only interpolates the first one and the last one. But it's important to see that it does interpolate the first one and the last one. Right? It's very, very important. And that's one of the reasons why these curves are actually quite popular. Another property is what's called the convex Hall property. That is, a Bezier curve is going to be contained inside the convex Hall of the control points. So convex Hall is the convex polygon in 2D that contains the control points. And the control points don't have to appear in order in this convex Hall. For example, if I had a different order of control points, I would have a convex Hall that looks more like this. And the Bezier curve is always going to be contained in this. And this is a very, very important property because we're going to, for a lot of applications, we use this property so that we can tell whether or not the curve is close enough by just looking at the control points without having to evaluate all points along the curve. Right? So this kind of gives us where the curve is. Another very important property of Bezier curves is that they are affine invariant. What do I mean by that? Here's what I mean. Remember I told you that when we have a function representation, if we rotate and we may not get a function, and that representation was not very helpful, the Bezier curves are actually very, very helpful in that sense. Because they're affine invariant. That means that if I take this curve that are generated by these four control points, and I apply some affine transformations to that curve. What are the affine transformations? We talked about them, right? We had translation, rotation, scale. I apply some translation, rotation, and scale, and my curve turned into this. So instead of generating this curve and then applying this transformation to the curve, I can apply the same transformations to the control points. And these transformed control points will define exactly the same curve. So by applying transformations to my control points, I haven't changed the shape of the curve. The curve is still the same curve. And that's a very, very important property, because this means that I can easily transform these curves, right? So I can apply all sorts of affine transformation to these curves. All I gotta do is to apply the transformations to the control points, and the curve is just going to be the same curve. So I don't have to generate the curve and then apply transformations later. This is a very, very, very important property. It's almost like a required property for a lot of things we do in computer graphics. We must have an affine invariant representation, and Bezier curves are affine invariant, so that's great. I also would like to talk about derivatives. Let's do some calculus. Huh? Who's up for some calculus? Yeah, let's do that. Okay, yeah, let's start with something a bit more familiar. Now, if I had a function representation, let's say this is a function y is equal to f of x, right? The derivative of that function, by that I mean derivative with respect to x, the derivative of that function is going to give me what? It's going to give me the slope, right? It's going to give me the slope of this line. It's going to be a scalar value. It's not going to be a vector or anything. It's going to be a scalar value that represents the slope of this line. So if it is flat, the slope is going to be 0. If it's vertical, slope is going to be infinity. It's going to give me the slope of that value, right? But we're not using functions like this because functions were a little restrictive. So we would like to represent things in parametric form. So if I draw the same curve in the parametric form, in this case, it's a function of t that spits out a vector. The derivative of this is going to give me not the tangent line, but it's going to give me the direction of the tangent line. It's going to give me this direction vector. Right? So, because this is a vector function, the derivative of this vector function with respect to t, with respect to its parameter, is going to give me the direction of the curve. So at any t value, this function will tell me where the position is, and this derivative function will tell me what this direction is. And this is very, very helpful, and we're going to use this property a lot for a lot of things. When I want to know where the curve is going, I just need to look at the derivative of the curve, right? And so if I can compute the curve's derivative with respect to t, that's very important. When I talk about the derivative of a parametric curve, I'm talking about the derivative with respect to its parameter. That's going to give me the direction of the curve. So if you look at the derivative of Bezier curves, so a cubic Bezier curve, which is a third-degree polynomial, looks like this. If I take the derivative of this curve with respect to t, I'm going to get, it's a third-degree polynomial. You're taking derivatives of polynomials many times, right? That's fairly easy to do. If I take the derivative of this curve, I'm going to get, it was a third-degree polynomial, it's going to become a second-degree polynomial. And if I shift things around a little bit, it's going to be a quadratic Bezier curve now. So from a cubic Bezier curve, its derivative is going to be a quadratic Bezier curve. Now, there's a little bit of a distinction here, though. I would like you to understand that distinction. Remember when we talked about vectors, we said that vectors can represent two distinct type of things. They could represent positions, they can represent directions. Now, this curve is representing positions in space. This curve is representing directions, not positions. But of course, I could interpret this as directions that draw this curve. No one can stop me if I wanted to do that. But the meaning of this curve is actually the directions along this cubic curve. Okay? And I can actually go in the opposite direction as well. I can take the integral of this curve. So I can actually generate this curve out of that, although not exactly, because there's going to be a constant term, but I don't know where the curve is going to be. But from its directions, I can generate the shape of the curve. So that's going to be the relationship between the cubic Bezier curve to a quadratic Bezier curve that represents its directions. Well, this was the first derivative. I can go further. I can take a derivative of this. If I take the derivative of this, then I'm going to get the second derivative. And guess what? That's going to be a line. Yeah, if this was a second degree polynomial, I get a first degree polynomial here. That's going to be a line, and I can, by shifting things around, I can represent it as in this linear interpolation form or a first degree Bezier curve. All good? All right, so we'll get back to that in a little bit. This derivative relationship is going to be important in a little bit. But before we get there, I want to talk about something else. First of all, let's thank this guy, Pierre Bezier, who was an engineer at Renault. He was a French engineer who developed these Bezier curves. And the problem that he was dealing with at Renault, if you haven't heard of Renault, it's a European car manufacturer. And at the time, they were trying to design curves for modeling cars. And they needed to have some representation of this shapes of these curves. And that's how this was developed. But at the time, this was late 50s, early 60s, I believe. Or we're not talking about the computers of today, right? So we're talking about curves that you could maybe draw by hand if you needed to. And actually, around the same time, when Pierre Bezier came up with this idea of the Bezier representation of the curves, there was another French engineer and another car manufacturer, Citroën, Paul de Castelnau, and he actually came up with the same idea. They had exactly the same idea around the same time. Although we call the curves as Bezier curves, de Castelnau actually had the same idea. So we should give him credit as well. Even though we typically refer to these curves as Bezier curves, maybe he should get credit. But we talk about something very specific. We talk about the Castelnau's algorithm for drawing these Bezier curves. Now remember, we're at 1960s or maybe late 50s. We want to be able to draw this curve maybe by hand. Now I'm saying that I define this curve using these 4 control points. These Bezier control points. De Castelnau had the same thought. But he also had this very nice algorithm for drawing them. And the way that he would draw them is as follows. Now, let's pick a t parameter, okay? Some t parameter. What I'm going to do is I'm going to take this line segment and I'm going to split that line segment somewhere down the middle based on this t parameter, such that, so this will be t units and the rest is going to be 1 minus t units. So I'm looking at the length of this line segment, and I'm splitting it such that this is proportional to t, and this part is proportional to 1 minus t. Okay? I'm going to do the same thing for this line segment. I'm going to split it down the middle such that this part is proportional to t, and this part is proportional to 1 minus t. Now I'll continue to this part. T, 1 minus t. Alright, so what did I do? I basically, from 3 line segments, I got 3 points. So I originally had 4 points, now I have 3 points to think about, and I'm connecting these two. I'm connecting the 3 points using 2 line segments. Here, I'm going to do the same thing. I'm going to take this one, and I'm going to split it again with the same proportion. T, 1 minus t. Over here, t, 1 minus t. Alright, so I did that. Now I had 3 points, now I have 2 points. Now if I draw the line between the two, you might notice that this line is tangent to my Bezier curve. And it's not just tangent to the Bezier curve. If I split this line using the same proportion, t, 1 minus t, this is a point on that Bezier curve. And this point is exactly the point that corresponds to ft, whatever that t value is. Right? So for a given t value, you can find that point on the curve using the Castel-Gilles algorithm, and you can do that by hand if you want to with a ruler. Fairly easy to do. So a brilliant algorithm, and the Castel-Gilles gets credit for this algorithm, although we typically refer to the curves themselves as Bezier curves. And some people like to call them Bezier de Castel-Gilles curves or de Castel-Gilles Bezier curves. Now, this is very good, right? This is very nice, very helpful, but there's something else that is very nice happening here. Very important too. Now, if you pay attention, this is a point on the curve, right? And over here, you see these 4 control points, starting with P0. There's this one, and then this one, and then this one. These 4 control points actually define this piece of the curve. And these other 4 control points, this one, and this last one, they define this remaining piece of the curve. So what I ended up doing is that I took a cubic Bezier curve and I split it into 2 cubic Bezier curves. So this is the subdivision process. I can split a Bezier curve wherever I want. Just pick the t value and I can split it at that point. And this is a very important property of Bezier curves. And using the Castel-Gilles algorithm, we can actually very easily do this. We can actually very easily compute these control points. Get a Bezier curve, we can split it in as many pieces as I want. And we're going to do that a lot, actually, for rendering the curves.
So what happened here is that I ended up splitting this Bezier curve into 2 cubic Bezier curves, one over there and one over here. And this splitting algorithm is used by a lot of graphics algorithms that handle Bezier curves for all sorts of different purposes. Because if I keep splitting this curve into smaller and smaller pieces using this algorithm, the pieces that I'm going to be left with are going to be closer and closer to linear segments. And then at some point I can approximate them as linear segments, and this is something that is used with a lot of algorithms for approximating Bezier curves or for computing different properties for Bezier curves. All right, so this is the Castel-Gilles algorithm. This is great. It works great, and it helps us split the Bezier curves, and it's actually used for other purposes as well. You could use it for modeling. If you want to add an additional control point here on the curve, you can do that using the Castel-Gilles algorithm. So it's very helpful, very nice algorithm. It's over there. All right. So the last thing I want to talk about today is going to be piecewise polynomial curves. So if I want to draw a long curve, a very long curve, what am I going to do? I'm going to need a lot of control points, so defining the shape of that long curve, right? If I have lots of details along that curve, I'm going to need lots of control points. But if I keep adding more and more control points with Bezier curves, I'm going to need higher and higher degree polynomials, which is not something that I necessarily want. We talked about this, that degree 3 was pretty good. Degree 3 polynomials, cubic polynomials were pretty good. So I want to be using cubic polynomials. But with a cubic polynomial, I'm going to have 4 control points. These 4 control points is going to define a curve like this that interpolates the first control point and the last control point, and the control points in between will just determine the shape of the curve, right? If I want to have a longer curve with more control points using cubic polynomials, what I can do is just to add another piece like this right after that one, right? So the curve starts over here, and this piece is defined by the first 4 control points, and the following piece is defined by the next 4 control points, right? So of course the question here is that, all right, attach this curve and that curve together, forming a curve here, but is this curve continuous? Well, there are different levels of continuity. First of all, the two curves are touching each other at this point, right? At this point, when they join, they are continuous. More specifically, they are C0 continuous because they are touching each other at this point. C0 continuity means that the curves are touching each other where they join. So they're not two separate curves. They're actually curves that are touching each other. And this is accomplished easily by using the same control point for both curves. So the ending control point for the first curve is going to be the beginning control point for the next curve. So that was fairly easy. This is called C0 continuity. If this is C0, do I have C1? Yeah, I do have C1. C1 talks about the direction of the curve. So the direction of the curve at the point where they join should be continuous if the curve has C1 continuity. More specifically, direction, that's the tangent, that is the derivative of the curve. So if the derivative of this first curve piece and the second curve piece at the point where they join, if the derivative is the same at the point where they join, then the curve, we say, has C1 continuity. Now, a lot of times I care about the direction of this derivative, but I don't necessarily care about the magnitude of this derivative. Because remember, the derivative is just going to be the derivative of the polynomial function, and I am interested in this direction to be continuous, but the magnitude of this derivative will depend on the parameterization of the curve. So how fast the parameter is moving along the curve. The magnitude of this derivative will depend on how fast the parameter is moving along. So I may or may not care about this. So if I don't care about this, I might have two different derivatives on either side, but with the same direction. So if the derivative is different in magnitude, but the same in direction, then I say the curve has G1 continuity. So in this case, I have the same derivative direction, but not the same derivative magnitude, because the parameter is moving a little faster on one of these curve pieces than the other one. But this is something that can be easily remedied if wanted to. So if given any G1 curve, any curve with G1 continuity, I can reparameterize its curve pieces to make sure that it is going to be a C1 curve. It's going to be a curve with C1 continuity. So these are somewhat easy to convert from G1 to C1. Any C1 curve is, of course, also G1 because, well, the direction has to be the same if the derivative is going to be the same. So C1 implies G1. G1 can be converted to C1 using reparameterization. All right, so this is G1, C1. Can we do C2? C2 would mean that the change of this derivative, the change of this direction is going to be continuous. That means the second derivative is continuous. So the change of this direction along the curve is going to be continuous as we move from one curve piece to the next curve piece. Similarly, I can have G2. That means the second derivative direction is continuous, but not the magnitude, right? And G2 would mean curvature continuity. That's why we care about it so much. If you don't remember what curvature is, let me quickly tell you. So at the point where they join, I can fit a circle. I can fit a circle that is tangent to this point, and the radius of the circle determines the bending of the curve at this point. So that defines the curvature. Actually, curvature specifically is 1 over this radius. Now, 1 over this radius is defined as the curvature. So that's a measure of how much the curve is bending at this point. So if the curve is perfectly straight at that point, then this radius is going to be infinity. So the curvature is going to be 1 over infinity. It's going to be 0 in this context. Right. So it's a measure of curve continuity. And this is something that we care about. So we care about C0 continuity. That means that curve pieces are touching each other. We care about C1 continuity. That means the direction is continuous. We also care about curvature continuity and thereby C2 continuity, because C2 continuity would mean that the bending of the curve is continuous. And this is something when you look at a curve, you can actually see if its bending is continuous or not. If there's enough discrepancy, you can actually notice it. But beyond C2 or G2 continuity, we don't necessarily care about, let's say, C3 continuity. We don't necessarily care about the third derivative to be continuous so much, because that's not going to produce something that's going to be visually identifiable. It's very hard to tell if the curve has C3 continuity just by looking at it. You might be able to say by looking at a curve, you might be able to tell whether or not it has curvature continuity. Even that is kind of difficult to tell by looking at the curve. C1 or G1, you can probably tell. C0 definitely, if their pieces are not touching each other, you can tell. So, but beyond this, we don't care about it too much. So we typically think about C0, C1, and C2 continuity in computer graphics, or G1 and G2 continuity. All right. So anyhow, the point is that what I would like to do is to have a piecewise polynomial curve, a long curve with some details, and I will need a whole bunch of control points to define that. And the way I'm going to define this is that I'm going to do this piecewise. So each piece, I'm starting with the first piece, is going to be, if this is a piecewise cubic curve, it's going to be defined by 4 control points. And the next piece is going to share this last control point, and it'll be defined by 3 other control points. And of course, I'm going to carefully place this control point such that I am getting the desired continuity over here. And then I pick the next, I add 3 more control points, I get the next piece, and then I define the next piece, and then the next piece, and then the next piece, and then the next piece, and so forth until I reach the end of the curve. All right, so this is the concept of piecewise polynomial curves, so that I don't have to use a very, very high degree polynomial to define a curve with lots of control points like this, right? And this is just one example of defining piecewise polynomial curves. There are different ways of defining piecewise polynomial curves that will help us with achieving different levels of continuity, and that's the stuff that we're going to be talking about next time. So I'm going to be ending this lecture over here at this point. Next time, we're going to talk about different curve formulations and how we can form piecewise continuous curves with different nice properties. All right, so let's end it here. Thank you all for